Good afternoon. It's my pleasure to be a part of this virtual math fest. And although I was not following it online, I'm still, like following it over YouTube. So thank you organizers to create, a very good platform for every one of us to have some informative sessions. So today's session on analysis and PD, we will start with Dr. Sayan Bagchi from IISER, Kolkata. He is a good friend of mine who finished his PhD at IISc, and he's going to talk about sparse domination technique and spherical maximal function. So Sayan, here we go.
Thank you, Rani, for introducing, and thanks to the organizer for introducing this conference. So Emma, is my screen visible?
Yes.
Yes.
Yeah. Okay. Okay, so I talk about sparse domination and the spherical maximal function. So mainly the second part of this lecture will be based on my joint work with Saurav Hait, Luz Ronkel, and Sundaram Thangavelu. So in the first part, I used to briefly give a survey of the sparse domination technique, and then you go to spherical maximal function. So let's start with this Hardy-Littlewood maximal function. This is a very well-known operator. It is defined like this. So given a function f locally integrable, we can define this maximal function by taking the average over mod f over cube and then taking supremum over all cube which contains x. And it is well known that this maximal function is bounded on LP Rn for 1 less than p less than equal to infinity. And that's what one can prove this by Marcinkwage interpolation theorem. The question is that what happens if we, instead of taking this unweighted space, we put some weight Wx here. Can we characterize all such W such that this weighted inequality is satisfied? And actually the answer is yes, it is possible to characterize all these W such that this weighted estimate holds. And those weights are called AP weights. So a locally integrable function W greater than 0 almost everywhere is called AP weights for 1 less than p less than infinity if WAP is defined like this. So we are taking supremum over all cube Q, and then we are taking average over W, average of W over Q, and average of W to the power 1 minus P prime. P prime is the conjugate of P, and then to the power P minus 1. So if this thing, supremum over this supremum is finite, then we call this W is a AP weight, and this quantity is called the AP norm of W. And then there is a famous theorem of Markov, which says that if W is in AP for 1 less than p less than infinity, if and only if the Hardy-Littlewood maximum function satisfies this weighted estimate. So here you can notice that we have put this Wx here, and this W is coming from weight. Okay. So in 1993, Berkeley proved that this constant actually is given by this, and this is the best possible constant. So this power this power 1 by p minus 1, this one cannot improve. This is the best possible constant. And for example, if you take p is equal to 2, then this becomes 1. So for example, for L2 case, this becomes WA2. Okay, so now the next slide. Now let's come to this very famous Calderon-Zygmund operator. So how it is defined? So suppose this delta is the diagonal set in Rn cross Rn, that is x comma x, and T is a bounded linear operator on L2 Rn, and K be a function defined on Rn cross Rn minus this diagonal, such that if you take any function in L2 Rn which is compactly supported, then Tfx is given by this integral for all x which doesn't belong to the support of A. And further, if this K, this kernel, satisfies these three properties, this first condition is called size condition. It says on the modulus of xy is dominated by this thing, 1 by x minus mod x minus y to the power n. And the other two properties are called Harmonic condition. So here we are taking, fixing the first variable x and changing the second variable. Here we take y and then z and take the minus modulus of that. Is satisfying this estimate for if mod x minus y greater than mod 2 y minus 2 mod y minus z, and the similar estimate if we fix this y, the second variable, then this operator is called a Calderon-Zygmund operator. This is a very well-studied operator, very well-known operator in harmonic analysis. And I mean, it is well known that these operators is LP bounded, and then from here this whole Calderon-Zygmund theory, so-called Calderon-Zygmund theory in harmonic analysis starts. It is also, one can prove, I mean, this is well known for a long time, that this CJ operator satisfies these weighted estimates with this constant depending on W. And this generally proves, one can prove by using soft maximal function, and very well known, maybe part of many graduate textbook. What was not known is that what is the best constant for this inequality. And that was a long-standing open problem for a long time. It was conjectured that the best possible constant, this is given by this maximum of 1 and 1 by p minus 1. And this was actually one of the famous open problem that was existed earlier in harmonic analysis. So this inequality, it is enough to prove this inequality actually for p is equal to 2, because then there is an extrapolation theorem in harmonic analysis which gives this result for all p. So if you prove this for p is equal to 2, it is sufficient. And that's why this conjecture is also known, was also known as A2 conjecture. Okay, so some important development thing. So Alford-Berling operators, which is a example of Calderon-Zygmund operator. It was solved first by Peter Mitchell and Holberg in 2002. Then for Hilbert transform, it was solved by Peter Mitchell in 2008. Rich transform, again by Peter Mitchell in 2008. And there are other results, I am not going to that. And then finally, for Calderon-Zygmund operator, it was proved by Thomas Hutton in 2012. So in 2016, Andre Lerner gave a very simple proof of A2 conjecture using this Sparse domination technique. And that's we will discuss now. So what is the Sparse domination technique? So first we define this sparse collection of cube. So sparse collection of cube is defined this way: a collection of cube, this S, so this is the family of cubes, in Rn is said to be eta sparse if for each member of this family there is a set ES which are pairwise disjoint and satisfy this estimate. Now to understand this, so let's take an example. So you take a cube and then you subdivide that cube into 4 parts by just joining the middle point of opposite side. Then you can divide this cube into the fourth part. And suppose your initial cube is S1 and is a member of the family. So you break S1 in 4 parts and say choose one children, one child as your and rename it as S2. The other 3 cube, the union of other 3 cube, you declare this as ES1. Now you come to S2, you again subdivided this in 4 parts. Choose one part and take it as a member of the family, and the other 3 part you describe it as ES2. And then you can go in this way, and then what you get a half sparse family, or I think 3×4 sparse family. So this is a typical example of sparse collection of cube. And again, so I use this notation. So given in a cube Q and 1 less than P less than infinity, this QP average of F is defined in this way. So we take mod of F and then take the average of over Q and then take the exponent of 1 by P. And if P is equal to 1, I just simply write this as this F of Q. Okay, so there are 2 operators generally used in this context. One is PQ sparse form, which is defined in this way. So here, this is a sparse collection, and this PQ sparse form is this. So we are taking F and G2 for function, and then this sum here we are taking the SP average of F and SQ over Q average of G, and then measure of S, and then sum over S. So this is one, this is called PQ sparse form. And also there is a sparse operator, which is defined in this way. So here we take the QP norm of F, and then characteristic function of Q X, and then sum it over all collection of sparse Q. So these are 2 operators we use. And so what is this, the learner's result? So the learner's proof, that's the first, that ARS, that is the sparse operator we defined. It satisfies this, so there's a typo, it should be LPW. So this, the LPW norm, the weighted LP norm of ARS of F is dominated by this. So here you can see that this exponent is maximum of 1 by P minus R, which is the best possible constant for Calderon-Zygmund operator. And this is true for any eta sparse family A. So this constant doesn't depend on the family, this constant C. Okay, so then the learner proved that if T is a CZ operator, then for every compactly supported function F, there exists a sparse family A such that TFX is pointwise bounded by this quantity, this sparse operator. And the sparse family S is may depend on this function F, but that doesn't matter because ultimately we have to calculate the LP, weighted LP norm, and this constant is independent of the sparse collection. So once we can establish this inequality from this theorem, one can easily prove the auto conjecture. Okay, so once this sparse domination technique is discovered, people started to trying to apply this technique for various other operators in order to get these sharp weighted estimates. So, and there is a huge number of papers written in this direction. I'm not giving the survey of that because that is impossible to impossible to give. I just give one important operator. This is called a rough singular integral. So suppose your suppose omega is a L infinity function on a sphere, and suppose this average of omega over sphere is 0. Then you have then the rough singular integral is defined in this way. Here, PV stands for this principal value, which is coming from the distribution theory. And then we have this. So this is the kernel, omega y by mod y to the power a. So this is the kernel and this is the operator. In 2017, Euclidean, Roncal, and Tapiola proved this estimate. And this estimate so that the weighted L2 norm of this is bounded by this thing. So here you can see the dependence on the weight. Here we are getting the A2 norm of W square. So if you can remember that for this Calderon-Zygmund operator, this power was 1. But here in this result, the power is 2. And that one can expect that this result may not be solved. So one can conjecture that maybe the true best possible constant should be this WA2 norm without any power or power 1. And there is a result in support of this thing that's given by Lerner, where he proved that if you take the composition of these two operators, this m is the maximal function and P omega is this rough singular integral. So if you take the composition of these two operators, then what you get, again, this W, this is A2 norm of W square, but here we are taking composition of two operators, and M already gives, we know that gives the, satisfy the weighted estimate with the norm of WA2. So one can expect that T omega will also give, satisfy the L2 weighted estimates with WA2 with power 1. So that's why one can expect that probably this conjecture is true, but still till now this conjecture is open, and I think one of the main open problem in this area. Again, all the proofs are given here is using this Sparse domination technique. Okay, so now we go to this spherical maximal function on Rn. So suppose sigma r is a normalized spherical normalized surface measure on the sphere of radius r. Then this we will consider this following spherical average. So ARF is basically the convolution of f with this spherical measure, which is defined by this. And then one can define this spherical maximal function by taking the modulus of ARF and then taking suprema over r greater than 0, which is this. So in 1976, Stein started this spherical maximal function, and it is bounded on this LPRN. He proved that it is bounded on LPRN for n greater equal to 3 if and only if p is greater than n by n minus 1. For n equal to 2, this problem was open for a long time. And then in 1986, Bourgain solved this this case for p is equal to 2, n is equal to 2. The main problem was that here we do not have this. So if you see this p, if n is equal to 2, then you can see that this is p is greater than actually 2, and that creates the problem. Okay. So now we come to the definition of lacunar spherical means, and here you can see that we are taking the suprema over all r greater than 0. For lacunar spherical mean, we take suprema over all 2j's, and j belongs to the integer. It is so in 1979, Calderon proved that this operator is actually bounded on LP Rn for 1 less than P less than infinity for n greater equal to 2. So when check, see the difference here. For full maximal case, we have boundedness for only for P greater than n by n minus 1. But if you take the lacunary, we have boundedness for all P. And this is because since we are taking over supreme over much smaller set, this quantity is much smaller than the full maximal function. So recently, this Michael Lacey revisited this problem, the spherical maximal function, this lacunary maximal function, and using Sparse domination technique, he reproved the Stein's and Calderon and Bourdieu's result, and also prove a quantitative weighted estimates for the spherical maximal functions. Then, if you have two functions f and g, and we have the maximal function of f. If you take the inner product of g, is
Yeah, I guess there is some disturbance in the sound.
Yes, I think there is some problem with his network.
Maybe a headphone is some loose connection or something.
Can you hear me?
Your voice was breaking a lot, Sayan.
Okay, just a minute.
It's better now a little
bit. Is it?
And is the headphone connected properly? I mean,
yeah, let me see. Is it okay now?
Yeah, I think it's better now.
Okay. Okay, so shall I continue from here, or I go back a little?
Maybe one slide back, and maybe you can present like Control L your PPT as well.
So from this slide, maybe, or maybe
Yes,
I can start
sure.
from. Maybe I can start from the spherical.
Yeah. I think yes.
Okay. So we start with again with the spherical maximal function. Suppose we have a surface measure. We have a surface sigma is the surface measure of the sphere of radius r. Then the spherical averages is given by this quantity ARF is actually convolution of f with sigma r. And then one can define the spherical maximal function by taking the modulus of ARF and then taking supremum over R. So this spherical maximal function is was introduced by Elias Stein in 1976, and he proved that this spherical maximal function is bounded on LP Rn for n greater or equal to 3 if and only if p is greater than n by n minus 1. And for n equal to 2, this problem was open for some time. Finally, it was fixed by Bourdieu in 1986. Now one can come to the lacunary spherical maximal function. Here we are taking supremum over all lacunary point 2 to the power z, all the dyadic integers. And was proved in 1979 by Calderon that this lacunary maximal function is bounded on LP Rn for all p satisfying 1 less than p less than infinity. So one can see that we get a bigger range of P because this we are not taking supremum over full R, so this quantity is much smaller than full maximal function, and that's why we get a better result. Michael Lacey has revisited this spherical maximal function problem using this Sparse domination technique, and actually reprove the result of Stein, Calderon, and Bourgain, and also give a quantitative weighted estimates for these maximal functions, spherical maximal functions. So here is his theorem. So suppose Ln is a triangle with vertices 1, 0, 0, 1, and n by n plus 1, n by n plus 1. Then this F and G, which are bounded and compactly supported, if we take two functions which are bounded and compactly supported, then there exists a sparse collection which satisfies this inequality. So we are taking the Lyapunov maximal function of F, and then take inner product, L2 inner product with G, and this is dominated by constant times the PQ sparse form of Fg. And this is that for all 1 by P, 1 by Q belongs to this triangle. So this triangle is actually looking like this. So if 1 by P and 1 by Q lies in this region, then one has this sparse bound. So the similar analog for full maximal function also proved by Lacey, and in that case the triangle is replaced by some another trapezium. Okay, so we have considered this problem for Heisenberg group. So Heisenberg group is basically Cn cross R, and then we have this group operation. We have ZT composed WS. In the first Cn variable is just an addition, and then the last variable, it is T plus S plus half of imaginary part of this. And this term make this group a non-commutative group, and it is an example of two-step nilpotent Lie group. Okay, so here also one can define a one can consider the surface measure mu r, normally surface measured for Z is equal to R. We take this surface Z is equal to 0 mod Z is equal to R, and suppose our measure is supported on this. The measure is actually surface measure of this. Then one can consider the associated spherical means, spherical maximal function in this way. So we take this F, convert with mu r is S, and then take supremum over all R. So this function was, this spherical maximal function was first considered by Nebo, Amos, and Thangavelu, and then Narayan and Thangavelu, and Muller and Seeger. So this is the result of Narayanan and Thangavelu. It says that M is bounded on LPH, and if and only if P is greater than 2n by 2n minus 1, provided this n greater or equal to 2. And this n is equal to 1 is still an open problem in this area. So one can check that this actually given by this Euclidean dimension of Heisenberg group. Okay, so now one can define this Lyapunov spherical beams. So here also we can, instead of taking supremum over all R, we can take the supremum over all dyadic integer. And so it was not considered earlier, and our main objective was to use this Lacey's technique of Sparse domination, and to prove an LP LP boundedness for this maximal Lyapunov maximal function and also to get some weighted boundedness. So here is the theorem we get. So suppose 1 by P, 1 by Q belongs to this triangle, interior of this triangle, this 0, 1, 1, 0, and n by n plus 1, n by n plus 1, these are same triangle of Lacy. Then we have this estimate. I mean, for any completely supported bounded function fg, we have a sparse family such that this estimate follows. So one can assume that so here actually that one can define this cube. For Heisenberg group, there is an abstract way of defining dialectic cubes by Michael Christ. I mean, that's given by Michael Christ, and so that way one can actually define a sparse family. So one can expect that this triangle is not a very sharp triangle, because here this is same as the Euclidean, it matches with Euclidean dimension, I mean the dimension of Rn, but we should get a better estimate. It should be 2n by 2n plus 1 and 2n by 2n plus 1, something like that. And we do not get this sharp triangle because of technical reason. So so in proving sparse bound, we of course closely follow this Lacy's technique, but of course for Heisenberg group there are some additional challenges, and we have to deal with that. So first, let's review this Lacy's proof and what is the idea. So the Lacy's proof is basically depends on two main ingredients, and the first ingredient is LP improving property of AR. That means he proved this LP-LQ bound for this ARF, which we'll come to in a while. And then there is a continuity property of AR, and that means that we will estimate this AR minus tau y AR, where tau y is the translation operator. And once we get these two estimates, there is a way to get the sparse bound for the spherical maximal function. So here is the LP improving property proved by Stickers and Littman, which says this. So suppose Ln prime is the dual of the triangle we defined earlier. It is 1 by P, 1 by Q, where 1 by P, 1 minus 1 by Q belongs to Ln. So this is the triangle we're talking about. So here it is 0, 0, 1, 1, and in by 1 plus n, 1 by n plus n. So if 1 by R and 1 by S belongs to this triangle, the triangle I have shown, then AR satisfies this estimates. Okay, so this R and this R are different. So this AR is bounded from AR to ALS. So just as proof of this estimate. So here we can use this something is well known in harmonic analysis called Stein's interpolation theorem. So if we take the Fourier transform of ARF, this is given by this formula, this the Bessel function, and by this, and this is bounded for if you take this. Okay, sorry. So ARF, the Fourier transform of ARF is given by this, and in order to apply this Stein's interpolation theorem, we have to extend this operator, and we can easily extend this operator analytic to get an analytic family of operator, and this can be obtained by this. So we just, instead of this Bessel function, we replace this by generalized Bessel function, this J alpha n by 2 minus R1. And then we define this operator as T alpha F. And it is well known that for real part of alpha greater than minus n minus 1 by 2, this function is bounded. So, this L2 bounded estimate follows from alpha is equal to minus n minus 1 by 2 by just applying this Plancherel theorem. And it is also bounded from L1 to L infinity, and thus that can be obtained by just observing the kernel. It is very easy to prove this estimate. And once we have that, we have the LP-LQ estimate, which is given here. So this is the LP-LQ estimate using this Stein's interpolation theorem. And then we have this continuity property. Continuity property says that so if we take A1 minus tau by A1, this is bounded for L to LS, where 1 by R, 1 by S are taken from the same triangle. Then it is bounded by, so this 1 by R, 1 by S is taken from the interior of this triangle. Then A1 minus tau by A1 is bounded from LR to LS with this decay mod y to the power eta, where eta is a number between say less than 1. And so this is the continuity condition. And once we have this continuity condition and the LP improving property, so actually LP improving property gives this continuity property. And once you have this continuity property, one can prove this Sparse bound. There is a way Lacey developed. Using that, one can prove the Sparse bound for the Lacanier spherical maximal function. Okay, so for Heisenberg group, we have this irreducible representation, which is called the Schrodinger representation, and this is given by given function L to Rn. The Schrodinger representation is defined by this. Here, this Z is basically is x plus iy, and y variable, the y variable act like a translation, and then we have this modulation factor. So one can prove that these are all the irreducible unitary representation of Heisenberg group, infinite dimensional irreducible representation for Heisenberg group. And then using that, one can define the Fourier transform for Heisenberg. Lambda is from R minus 0, and then by the lambda x.
Sorry to interrupt, Sayan. I think your headphone is again creating a little bit of trouble.
It okay now?
Yes, yes. It was only some sort of interruptions, so I think it should be fine now.
Okay, so one can define the Fourier transform like this. So here, as pi lambda is an operator on L2 Rn, this is also an operator on L2 Rn, f at lambda. And then one can, the spherical maximal function that we have defined earlier, one can check that the Fourier transform of ARF lambda is given by this multiplier, where mu r lambda is an operator, and that is given in terms of the spectral that's actually spectral multiplier associated with the Hardy operator. So Hardy operator is given by this minus Laplacian plus mod lambda mod x. So lambda square mod x square is the usual Hermite operator, you know. Then one can write the spectral decomposition like this. Here 2k plus n mod lambda is the eigenvalue of h, are the eigenvalues of h lambda, and then so this mu hat lambda is given by, so in order to define this mu hat lambda, one has to define certain special function called this Legard function, which is defined by this. So I'm not defining this, but this is our very standard in harmonic analysis out of the theory of special function. So once you have these functions, one can define mu lambda in this way. So here, instead of this 2k plus n lambda, we replace this by this psi alpha k. And this is called the Harmonic multiplier. And then one can prove that if real part of beta is greater than, so one can then similarly extend this operator as an analytic family of operator in this way. So here, instead of psi k, I take beta plus n minus 1. And then one can check that if beta greater than minus n plus half, then this t tilde beta, the analytic family that we defined, is actually on. The problem is to prove the other part, that is, so when we want to prove that when real part of beta is greater than 0, then this t beta is given by this formula, integral formula, and it doesn't seem to give any L1, L infinity boundedness for whatever large beta we can take, because there is some problem in this t variable. So in order to overcome this, we have to find a new, create a new family of operators in this way. So we take this k beta t by this, and then we take this function f, and then convolution with this k beta on this t variable, and then take this integral formula, and that is for beta. So you can say that here we are taking, instead of t tilde beta, we are taking convol f with this k beta. So that this multiply and this of, then we get this multiply, and this is also for beta. So this is for beta greater than minus n minus 1 by 2. This L2 bounded that one can prove by some work. And then we also have this this estimate, this L infinity L1 partial delta estimate for this family. And once we have this two estimate, one can, using analytic interpolation, one can get this LP-LQ estimate by this. So this is the result. If you take A1, so you take R is equal to 1, it is bounded from LP to LQ, whenever 1 by P and 1 by Q lies in this triangle. And once you get the A1, one can also get for AR using this dilation. And then one can prove this using that LP improving estimate. One can prove the continuity property by this. So first one have to prove that this A1 minus tau, if you take L2 to L2, then this is bounded, bounded by C mod Y. And this gives this continuity property, that's 1 by P, 1 by Q. If it lies inside this triangle, then we have this estimate. the A1 minus A1 tau y LPLQ estimate is bounded by C mod y to the power eta. And this proof is not as easy as Lacy's case. One has to do some work and one has to use the structure of Hn. So once I have this LP property and this continuity property, one can then try to the Lacy's proof, and one has to somehow develop this develop this idea for homogeneous type space, and then one can prove the sparse bound for this surface maximal function. And once this sparse bound, we get the sparse bound, we can prove the is a routine method to prove the unweighted norm inequality and the weighted estimates for Lagrange.
Thank you, Sayan. That was like wonderful collection of beautiful results. And it was good to see all in one, and the flow was very nice. So now let me see if we have any questions for the speaker.
Do you have uncertainty principle type inequalities or results?
For that, no, I don't. I haven't seen any result. Uncertainty principle and weighted inequality? No, I don't see any result.
Okay, all right. Thank you.
Thank you, Professor, for your question.
Very good talk. Very good. Very good.
Thank you.
Okay. Yeah, so let's thank Sayan.